film clip is to explain the trends in the melting points and boiling points for ozone and oxygen. From our table here, we can see that ozone's melting point is higher than the melting point of oxygen, which I've summarised here in this mathematical statement, and we need to explain that in terms of bonding. And similarly, the trend here, that the density of ozone, 1.6, is larger than the density of oxygen at 1.1. And I've got some little diagrams here prepared to show that. So with respect to melting points, we know that for something to melt or boil, it's got to be separated from its similar atoms of itself. So it's all down to the size of the attraction between the molecules. And there's two ways of explaining this. We know there is a trend in the periodic table. For example, when we go down the halogens from fluorine down to iodine, that we start as a gas, we go through the liquid with bromine, and we end up with a solid at iodine. Now, the attraction between the halogen molecules is just dispersion forces. So we came up with a statement on this evidence that the size of the dispersion forces gets bigger for bigger molecules. And just following that, we've got ozone's a bigger molecule than oxygen. So we'd say that the size of the dispersion forces, the attraction between molecules, is larger for the larger molecule as it was for iodine. And that's going to lead to the melting point of the larger molecule being bigger, because the attraction, the force you're overcoming, is larger. There are some books that also attribute the ozone molecule to being slightly polar, because you have a situation where the concentration of most of the electrons are this side. And that would lead to the same argument, that the forces between these molecules is larger because of the unevenness of the molecule, and that would be further evidence for the fact that the boiling point and melting point, the force required to separate these molecules, would be larger for the larger molecule. So it's to do with the nature of the bonding. With respect to density, again we have the same trend that the density of the ozone, the larger molecule, is bigger. We need to remind ourselves that density is mass divided by volume. So if we keep the volume the same, in other words the same sized box, really mass and density mean the same thing. So we're looking at now the mass. Now if you look at it, you need to remember Avogadro's law, and his law derived the idea of the concept of there being a certain size that takes 1 mole of gas. And his idea was that in a given size, you had the same numbers of molecules, irrespective of what they were. That reasoning led us to the idea of them being a size that would take 1 mole, or 6 by 10 to the 23 particles. So if I draw equal sized boxes, Avogadro's law says that there's equal numbers of molecules in both, because that's his rule. And we can see now that if we're taking out that variable, because we've got the same size or volume, then density is proportional to mass. And in here, we've got more mass for the bigger molecule with ozone than we have with oxygen. So hence, the density of the oxygen molecule is larger than the density of the density of the ozone molecule is larger than the density of the oxygen molecule. Thank you for listening.